In this class, we learn some theorems on groups. The first theorem, theorem number 3, read as let G be a group. Prove that AB whole inverse is equal to B inverse A inverse for all A comma B belong to G. Here we are discussing inverse of A dot B or A circle B or A star B. Here we write our convenience. We omit the symbol dot or circle or like that. I am writing AB instead of A dot B or A circle B or A star B. The symbol is understood. Students, please note this point. Somebody says it is a inverse of product of two elements. But I will say inverse of composition of two elements. Here we have to prove that AB whole inverse is equal to B inverse A inverse. I will explain this easily. Suppose AB is equal to X. That means we have to show that X inverse is equal to, call it some Y. We have to prove that X inverse is equal to, call it the right side part as Y. X inverse is equal to Y means, using the definition, we have to prove that X dot Y is equal to E and Y dot X is equal to E. Then we write X inverse is equal to Y. So that is the way to prove this theorem. Suppose this AB as X and right side part as Y, then the theorem read as X inverse is equal to Y. We have to show that X inverse is equal to Y. Using the definition, we have to show that X dot Y is equal to E and Y dot X is equal to E. Then we say that X inverse is equal to Y. So let us go to the formal proof. Let G be a group and E be the identity element in G. Always we write the symbol E for the identity element. Let A comma B belong to G. I am taking two arbitrary elements in the group. A comma B belong to G implies A dot B belong to G, A inverse belong to G, B inverse belong to G. And again A dot B belong to G and B inverse A inverse belong to G. I am using closure property for these two elements. A inverse belong to G and B inverse belong to G implies B inverse dot A inverse belong to G. Now, as explained in the statement, I will take xy and I will show that xy is equal to E and yx is equal to E. So, I am taking x and taking y. This is a simple using associative law. Change the brackets here. Use some other bracket, square bracket here. This is A, square bracket B inverse, A inverse, bracket closed. And again, use the associative law here. Change the bracket here for BB inverse. So this is read as A square bracket BB inverse A inverse. And we know that BB inverse is equal to E. So this is read as A square bracket EA inverse. Since E is the identity element, we can write A inverse. EA inverse becomes A inverse. So this is AA inverse. Again, AA inverse is equal to E. Thus XY is equal to E. And next we show that YX is equal to E. For that, YA. Y means B inverse A inverse. X means AB. Again use the associate law. Change the square bracket here. B inverse. Square bracket A inverse. Bracket AB is equal to. Again use the associate law. Change the bracket for A inverse A. So this is read as B inverse. Square bracket A inverse A. B square bracket closed. This is equal to. Here A inverse A becomes C. So I will write B inverse EB. Again I use that E is identity element. So this becomes B. So I will write B inverse B. And again this is E. Thus XY is equal to E and YX is equal to E. So this Y is called inverse of X. That means inverse of AB is B inverse A inverse. Symbolically we write AB whole inverse is equal to B inverse A inverse. So student understood like this one. Yeah, suppose this left side part is X inverse and right side part is Y. We have to show that X inverse is equal to Y. So from the definition we know that we have to show that XY is equal to E and YX is equal to E. Then we get this Y is inverse of X. So I am writing therefore inverse of AB is B inverse A inverse. Symbolically we write AB whole inverse is equal to B inverse A inverse. Next we go to theorem 4. It is known as cancellation laws hold good in a group. In our algebra, we know that there are cancellation laws. In a equations or something, we can cancel some number the left side part and right side part if there is an equation in algebra. So likewise, in the group also cancellation laws hold good. That means we can cancel an element from the left side or from the right side of an equation. We go to the formal statement of the theorem. Let G be a group. Then for A, comma B, comma C belong to G. The equation AB is equal to AC implies B is equal to C. And the equation BA is equal to CA implies B is equal to C. Observe that here on the left side of this equation, this is A, B and this is AC. This implies B is equal to C. That implies we can cancel A on the left side of the equation. And again here it is BA and it is CA. See that A is on the right side part. And this implies B is equal to C. That means we can cancel A on the right side. But don't use the symbol cross symbol and like that. Just write this as B is equal to C. Don't put a cross mark or any other for this to remove this A. Next, proof. Let G be a group and E be the identity element in the G. Always I am using that, I am saying that E be the identity element. Next, let us take three elements in the group G. A, comma, B, comma, C belong to G. A belong to G implies A inverse exists. So I will let A inverse belong to G. First take the equation AB is equal to C and operate A inverse on left side of this equation. So I will let A inverse bracket AB is equal to A inverse bracket AC. And using associate law, change the bracket. I will write bracket A inverse AB is equal to bracket A inverse AC. We know that A inverse A is equal to E. So I will write EB here. Here EC here. Since E is the identity element, we get B here and C here. So B is equal to C. Thus AB is equal to AC implies B is equal to C. Left side A is cancelled. Write simply like this only. Don't cancel. Don't put a cross mark on A. Similarly, second equation. BA is equal to CA implies. Apply A inverse on right side. Operating A inverse on right side of the equation. Bracket BA A inverse is equal to bracket CA A inverse. Using associate law, I will write B AA inverse is equal to C AA inverse. And AA inverse becomes C and here also. So this is BE is equal to CA. Since E is the identity element, we get B is equal to C. Thus BA is equal to CA implies B is equal to C. That means right side A is cancelled. Therefore, cancellation laws hold good in a group. Here it is called left cancellation law and here it is called right cancellation law. So both are true here. So I will say therefore cancellation laws hold good in a group. Next we see some other theorem. Prove that in a group G for A, comma, B, comma, X, comma, Y belong to G, the equations Ax is equal to B and Ya is equal to B have unique solutions. Here we are taking four arbitrary elements in the group G. Arbitrary means any four elements, not particular elements. And the equation Ax is equal to B has unique solution and the equation Y is equal to B has unique solution. We have to prove. It is a group and we are taking four arbitrary elements and we have to find a solution for Ax is equal to B and Y is equal to B. It is simply a guess. You can guess. Here, if we put X some value, we have to get B. So guess what is that X value? What is the X element we have to replace? Simply the result we have to be. So if we put X is equal to A inverse B, then we get B. And here also Ya is equal to B. What is the solution for Ya? Think in natural way. If we put BA inverse, if we replace Y by BA inverse, we get B. So always think in a natural way to find the solutions or the problems or proof of the theorems. Now we go to the formal proof. Let G dot be a group and E be the identity element in G. Let A B belong to J. I am taking two arbitrary elements in the group G. A comma B belong to G implies A inverse belong to G and B inverse belongs to G. A inverse belongs to G and B belongs to G implies by closure property A inverse B belongs to G and B A inverse also belongs to G. Take X is equal to A inverse B as explained in the statement. Take X is equal to A inverse B. Then AX is equal to replace X by A inverse B. And using associated law here, change the bracket for the elements A inverse. So this is bracket A inverse B. A inverse becomes E. So this is EB. Since E is the identity element, we get B. Thus, AX is equal to B as a solution A inverse B. Here X is replaced by A inverse B and the result is B. So I will write X is equal to A inverse B is a solution of the equation AX is equal to B. Next we go to the second equation YA. Second equation YA is equal to B. So consider, take Y is equal to BA inverse. Take YA. Replace Y by BA inverse. BA inverse A is equal to B. Use associated law and change the brackets for these two elements. So this is B bracket A inverse A. This becomes E. So this is BE. BE is equal to B. Thus YA is equal to B has solution. And what is the solution? BA inverse. Therefore I will write Y is equal to BA inverse is a solution of the equation Y is equal to B. But in the statement asked, so that unique solutions. Unique means only one solution. For the equation AX is equal to B, there is only one solution. And for the equation Y is equal to B, there is only one solution. We have to prove. So what happens if there are two solutions? Let us see. If possible, suppose x1, x2 are solutions of the equation AX is equal to B. Then AX1 is equal to B and AX2 is equal to B. Here this is B, this is B. So these two are equal. Here this is right side part B. Here right side part B. So left side part must be equal. AX1 is equal to X2. AX1 is equal to AX2. We are discussing this in a group. In a group, cancellation laws hold good. On the left side part, here it is A, here it is A. So we can cancel A. We get X1 is equal to X2 by left cancellation law. Here we have supposed there are two solutions. X1 is equal to X2 for the equation X is equal to B. And we have arrived that these two are equal. X1 is equal to X2. So there is only one solution for the equation AX is equal to B. Next, if possible, suppose Y1, Y2 are solutions of the equation Y is equal to B. Then we get Y1A is equal to B and Y2A is equal to B. Here it is B, here it is B. So these two must be equal. So I will write Y1A is equal to Y2A. And again we can cancel right side A. So we get Y1 is equal to Y2 by right cancellation law. Here also we are supposing Y1 and Y2 are two solutions of the equation Y is equal to B. And we arrived that Y1 is equal to Y2. So there is only one solution for the equation Y is equal to B. So I will conclude. Therefore, AX is equal to B and Y is equal to B have unique solutions in the group G dot. This is one important theorem in the examination point of view. The equations AX is equal to B and Y is equal to B have unique solutions. First, we have proved one solution, and we have next we go to the uniqueness of the solution. For the equation AX is equal to B, the solution is X is equal to A inverse B. And for the equation Y is equal to BA inverse, the solution is BA inverse. And we have proved that uniqueness of the solution. Therefore, AX is equal to B and Y is equal to B have unique solutions in the group G dot.